Associate Principal Dr. Tejinder Kaur Taliwal, Vice Principal Dr. Rana Baljinder, Dean Academics Dr. Nina Mehta, HOD Department of Basic Sciences Dr. Anita Rani, our respected speaker of today's talk Dr. Subhash Chandra Sahu, my colleagues and all dear participants, good morning to all. I, Kirandish Kaur, Assistant Professor in Chemistry, pleased to welcome you all to join the webinar on crystallography that is a part of a two-day national webinar on recent advances in sciences and its applications. First of all, I want to present a brief introduction about our college. This institution was started as Women College under the patronage of Sardar Prakash Singh Badal, ex-Chief Minister of Punjab, feeling the dire need of women education in this backward region of Malwa in 1970. The college is affiliated to Punjab University, Chandigarh and governed by Shromani Gurdwara Prabandhak Committee, Shri Amritsar, a supreme religious authority of the Sikhs. The college campus is sprawled in more than 14 acres and has a very pleasant and peaceful environment. The institute endeavors to make students globally fit by equipping them with the latest ultra-modern training in information technology and practical exposure to the students. As per the need of time, the institute becomes co-educational institution in 2020. In 2020-21, the three subjects of college, mathematics, physics, and chemistry, are selected under Star College scheme of DBT, New Delhi, to get financial assistance. This Star College scheme is provided by Department of Biotechnology, New Delhi, to financially support colleges and universities undergraduate providing undergraduate education to improve science teaching across the India. Its main aim to improve critical thinking and encourage hand-on experimental science in basic science subjects. Under this Star College scheme, the Department of Basic Sciences is organizing this a two-day national webinar on the topic of today's talk is crystallography, and the resource person, Dr. Subhash Chandra Sahu, will enlighten the participants with his wonderful experiences in this field of science. Let's brief introduction about our special guest is that Dr. Subhash Chandra Sahu is working as assistant professor in chemistry in Department of Chemistry, Center of Advanced Studies in Chemistry, Punjab University, Chandigarh. Dr. Sahu has done his PhD in chemistry and was CSIR Nehru Science Postdoctoral Fellow at National Chemical Laboratory Pune from 2011 to 12 and postdoctoral fellow at New York University from 2012 to 14. Since 2014 onwards, Dr. Subhash is providing his services as assistant professor in chemistry in Punjab University, Chandigarh. The sir has specialization in teaching in inorganic chemistry and has research interest in coordination chemistry, solid state, photochemistry, and metal organic frameworks. The Dr. Sahu has received number of academic honors for his research contribution in science. The sir has more than 12 years of research experience. The Dr. Sahu is member of many learned societies and academic bodies like patron member of Odisha Chemical Society and has life membership of Indian Crystallography Society. The Dr. Sahu has actively participated in number of seminars, conferences, workshops, and delivered special talks at national and international level. The Dr. Sahu has more than 60 publications in reputed international journals with high impact factor. I present a warm welcome again to Dr. Subhash Chandra Sahu to provide us his valuable time from his busy schedule. I believe that by participating in this webinar, we are in the right place and at right time. I am confident that you will find new ideas in this field of crystallography. Now I request our worthy principal, Dr. Tejinder Kaur Taliwal, to welcome our special guest of the day. Welcome, ma'am.
Hello. Unmute करना okay.
Hello.
Hello. Yes. Yes, ma'am. Yes, ma'am.
ओके जी ओके वाहिगुरु जी का खालसा श्री वाहिगुरु जी की फतेह on this gracious occasion I welcome Dr. Subhash Chandra Sahu ji, assistant professor in chemistry, Punjab University, and reputed scholar who has many distinctions in his name. I welcome Sahu ji. I welcome all the participants and congratulate Department of Basic Sciences for organizing this webinar on crystallography. As crystallography is an experimental science used to determine the crystal structure in terms of atomic positions, unit cell, and crystal symmetry, the crystallographer can also establish the new material's fingerprint, and crystallographer can help industry to develop new chemical products, including the agro-food, aeronautic, automobile, beauty care, computer, electromechanical, pharmaceuticals, and mining industry. The main objective of this seminar, I think, is to give the students a knowledge of the interaction of radiation and condensed matter, knowledge about instrumentation and for different diffraction methods and its general use in the outside world. On behalf of Guru Nanak College, I welcome all the participants, teachers, and students. I hope you will gain from the experience of learned scholar Dr. Sahuji, and I again welcome all the participants. Thank you very much.
Thank you, ma'am. This webinar on crystallography will include the special talk on X-ray diffraction of crystals, Bragg's equation, determination of crystal structure of many compounds, Lewis method, and powder diffraction methods, etc. Now I request Dr. Saho to share his talk with our participants. Welcome, sir.
Okay, so good morning. So am I audible, ma'am?
Yes, sir.
Okay. So, so first of all, thank you, ma'am, for short introduction of myself and you.
Welcome, sir.
College, and I thank the principal ma'am and HOD ma'am for the beautiful arrangement of this webinar and inviting me as a resource person for this talk. So hopefully I will give some brief introduction about the crystallography based on my so far more than 12 year experience on crystallography. So so without much delay, so I welcome all these participants, especially the students, I think. So may I know the students are from which background, ma'am?
Sir, BSc medical and non-medical, also the participants from other states.
Acha, okay, thank you. So I think as I can see, there are some non-medical students are there. So anyway, I have kept the entire talk in such a way that it will go to the all level of students who are present here, and they will get some basic idea of what is crystallography and what extent we can get the informations, and many beautiful things I will share during my talk. And hopefully this will be my entire outline will be 2 lectures, but don't mind, I'll not make you bored. Okay. And the first lecture I will cover some of the history and characteristics of X-ray, properties of light, basic X-ray diffraction, and followed by Bragg's diffraction and Laws method. And the second part of lecture, basically the application of the X-ray diffraction to get the structure of various molecules, and what extent we can go to use this diffraction for various applications. So, so let us start. All of us, you might have know what is the electromagnetic radiation. This is a wide range of there is some disturbances. Yeah. So the electromagnetic radiation is a huge range, starting from radio wave to gamma ray, and
किरण किसी ज्वाइन करके दो ना।
Dear participants, mute your mic.
हाँ सर का भी म्यूट है दे दो।
Sir, please on your mic.
sorry. Yeah.
Hello.
Hello.
Okay, sir. Now listening.
Yeah. So, so let us start. So thank you all for this invitation. And my outline of my talk is that the first lecture I will cover the history of X-ray, characteristics of X-ray, basic principle of X-ray diffraction, and Bragg's method and Lau methods. And then I will move to the second lecture where I will the basic pattern of X-ray diffraction and how we can get the structure of various molecules using X-ray method. And the electromagnetic radiation, we all of us we have familiar, and the electromagnetic radiation has a huge range starting from radio waves to gamma ray, and the wavelength varies a lot, starting from a radio wave which wavelength is almost size of a building to towards the right. If you go to the X-ray, the atomic the wavelength of the light decreases towards almost 1 angstrom, and the 1 angstrom is so short that we cannot develop any kind of lens, okay, or any microscope using that short wavelength and to see the structure of atoms. Okay, so there is the limitation occurs. So that people have started to discover that how to know the structure of a molecule, because it's so small and we cannot use any lens to identify some atoms. Okay, so there the history actually, and if you see the interaction of light with matter, it has a meaning. Okay, whether the light can interact with matter in form of transmission or absorption or reflection or scattering. Okay, and if you'll be surprised that based on all these in unique properties, all sort of instrumentation methods have developed. All these instrumentation method, they will follow one of these properties, whether absorption, transmission, or reflection. But our today topic, I am not going to cover all, but today we'll only cover how the scattering occurs, okay, and which is related to your X-ray. Okay, so it is a very beautiful correlation you can make, that any person, sometimes we need a lot of information from various sources, like from police, from institute, from collector, from hospitals. And if you see that all these, the same person is getting different information from the different interaction unit or offices. Okay, exactly same correlation you can make when the matter interacts with different type of lights, whether it is IR or UV visible or NMR or X-ray. we can get the different information of the same matter. Okay, so this is my own way of teaching my students, and this is a beautiful correlation you can make, that why different information we get from different lights. Okay, this just correlation, but again, because all the lights are not same, even though they are interacting with the same matter, but the light sources are not same. Okay, maybe the matter is same for all, but the interaction is not same. That's why the different information we get. Okay, the beautiful story of the X-ray actually started around 1895. Okay, in 1895, in the day of 18 November, and this is the William Rodgen. He was doing some experiment in his lab. As surprisingly, his wife actually visited his lab, and he was trying to discover the X-ray. He was working a lot many years before, though he got Nobel Prize in 1901. And during that experiment, he requested her wife to show her hands in the that X-ray, and suddenly he captured a beautiful picture of her wife, where the ring also came in the photograph, and they got surprised, and that was the breakthrough of X-ray discovery, you can say. Okay, and this is the 8th November, and you can correlate the day which day we observe World Radiography. Okay, the answer is very clear. This is 8th November because of the X-ray discovered on that day. Though it was working many years before of X-ray, and though she got a beautiful William Rodgen got a very good photograph of her wife, and that changed the entire work, fruitful of his work. But his wife actually got very much angry, okay, because she got scared by this photograph of that skeleton. Okay, and later she told that I have seen my death. Okay, in some statement. Anyway, so many stories actually associated with X-ray, and sometimes we feel that we get to think person who planted this tree, because X-ray was discovered. Many people, they don't know how to handle what is the impact of X-ray in bad impacts of X-ray. Okay, and you'll be surprised that many people died because of X-ray, using X-ray as research. Okay, one person, this is the first person, see, in Delhi, and this guy actually died just in the age of 39 because of high exposure of X-ray. Okay, because that time there was no idea how the X-ray will be harmful to body or later stages. So he died because of cancer. Many people died actually when the true usefulness of X-ray actually came into picture. Okay, and nowadays you'll be surprised that X-ray has extended to many applications in our day-to-day life, starting from security, medical diagnosis, food security, heavy industry, pharma industry, and medical analysis, and many more. Okay, and this is a huge application of X-ray. And another surprising information I want to share here. So far, I think not any other topic there will be highest number of Nobel Prizes in X-ray crystallography so far. Okay, so far I have given a total list of around 19 Nobel Prizes related to X-ray crystallography. They are directly, indirectly, starting from Rodgen, who got the Nobel Prize in 1901, and then Lau, then Bragg, then one after another. Even the our India scientist V. Ramakrishnan, who got the Nobel Prize in 2009, and all sort of these Nobel Prizes are somehow directly or indirectly related to crystallography, and all the information I have taken from this CCDC website. Okay, and this information you can highlight that how important this X-ray is now from the developed from 1901. Okay, and the first breakthrough using the X-ray, I can there are many people working on X-ray, how to use the X-ray for various applications, and I can say this the three peoples I can there are more credit goes to these three peoples. One is Maxwell Lau and the Braggs, the both father and son. And there is again another beautiful story behind this father and son. Both the father and son, they shared the prize in 1950. This is rare cases where both father and son they got because both the father and son, they are working on the same X-ray. And there is a beautiful story I am sharing here. This is 1912. This is original letter written by his son to his father. The dear dad, I did this experiment. He has drawn some pictures and he has written the results to his father. Maybe that time no communication or something. I don't know the exact way, but somehow he wrote his letter to father and explaining about the experiment. And the first diffraction they got the one zinc sulfide crystals and beautiful pattern they got, and he was explaining the entire story to his father. And somehow it was in 1912, but after 3 years the beautifulness of this studies actually came into light, and both the father and son, they got the Nobel Prize. Okay, and before that, before discovery of X-ray, if you see, a lot of actually things happen, and many tragedy actually happened to in world. One things I want to share, the cholesterol, it was known around 1800. Okay, but the true structure, initially people have thought of the left side structure, people have think of this is the original structure of cholesterol. But later, around 130 years, around 1930 only, because X-ray was discovered 1901, Bragg again around 1915. Then the X-ray structure was structure determination even after a long time after that. And because there was no NMR. NMR was discovered around 1945 and LCMS maybe around 1988. So the X-ray was discovered fast. So that's why there is no other way to establish the structure, and people have long time people have thought of that this is the original structure of cholesterol. But after around 1930, by doing X-ray structure analysis, the true structure of cholesterol, which is right, I have shown here, it was established. Okay, so this is the beauty of this X-ray. But I want one very beautiful another story I want to share. It's not beautiful, I can say, but this is a horrible story, I can say. This is a thalidomide tragedy. Actually, this is a drug actually used for various anxiety related or tension related patients. And after discovery of this medicine, many people have take these drugs. And after maybe 1 or 2 years, that a lot of actually babies actually born with their malfunction of their hands or legs. Okay, a lot of the people came to know, and that time it was not sure that the drug was tested very nicely, but why it is showing. But the problem came into picture because the drug has a isomer or R and S isomer. And isomer structures you cannot distinguish by either NMR or something. It's very difficult. It can only distinguish by X-ray structure if you get. And around 1915, the drug was stopped to use. And by the time, many people actually got malfunction in their hands and legs. And it was later came to know that the S-thalidomide, which is the isomer of this R-thalidomide, which is a drug actually, but the S-thalidomide is totally poisonous. Okay, it is create a poisonous character inside the body, and that's why it is not good. And only after the X-ray it was came to know. Okay, so anyway, so this is there are a lot of history actually associated with the X-ray, but again I am not going to touch upon all these. So few things just to highlight it, that how X-ray has developed, and maybe I'll share some of the very good journals. If you have time, you have interest, you can read those, and you will came to know there are many interesting things associated in the entire discovery of X-ray. Okay, so we'll move to the some another points. Remember, in my first lecture, I will discuss about many points. Okay, many dots, and later you will join all the dots to get a lot of information what we are discussing. Okay, because this is the crystallography. I think it is just one semester course, and just 2 lectures. It is very difficult to convey all the informations. But what are the essential information I am just sharing, and you just consider there the different dots, and we combine all the dots how to get the useful information. So constructive destructive interference. What is this? Because there are some waves, and the waves have when the similar type of waves having similar phases, okay, and the bottoms they are exactly matching. And when they are the similar type of waves, okay, exactly having similar phases, or in terms of physics term, you can say similar frequency. Okay, and this is called a constructive waves. Okay, that is wave addition. And there is another way. The below part you can see there are 2 waves. Again, I have shown, but their horns are not matching, and their gaps are not matching. Their where the upper one is horns and the below one is not there. Okay, so that means these 2 waves they are not in similar phases. Okay, and when the dissimilar waves actually they combine, we got a destructive wave, and here the amplitude has decreased a lot. Okay, and this is physics. Many of you might have learned this. Now, how we can correlate this? The correlation is very good, straightforward. You can correlate light, and you'll agree that we can focus a laser light to a longer distance. Okay, but rather we cannot focus a normal light to a longer distance, because many destructive waves are coming out from these white lights. Okay, they destroy each other, because of which the amplitude of this wave is so less that it cannot extend to a long distance. Okay? In the other hand, when there is a constructive wave functions, when there is a amplitude of the original wave is so high that you can focus the waves to a longer distance. This is the 2 example, great example of day-to-day life example of laser light and normal light. Okay, and we can say the conclusion that when the wave is monochromatic and single phase, okay, then the wave can transfer to a longer distance. Okay, and let us see an example. In a day-to-day life, you can go to any ponds and just put some stone in this ponds, and you'll see the ripples are creating and they are expanding to the bank of this ponds, and that the wave where it is created, where your stone has hit the ponds, and the ripples has created from there, but all the waves are reaching to this bank of this pond because of the constructive waves. Okay, and there is, if there is no constructive waves, the waves cannot reach to this bank. You can see I am sharing another photo from website, from Google actually. This is a high school winning photo. Okay, and I asked some of the students, let us ask whoever the present here, I'll just to make some interactions. Okay, I'll Navjot Kaur, BSc 2. Can you hear me? Hello, Navjot. Okay, that maybe they're just listening. Okay, so my question is here: what is the beauty in this picture, that this photograph is a high school winning photo? Okay, and this answer is here. If you can correlate, in this photo there are a lot of your constructive waves and destructive waves they are forming here. Okay, And if you see the two dogs in the two sides, the all sort of constructive waves are going on, but the middle parts, you can see the waves are breaking here. Okay, they're dying. Okay, because the two waves, they're coming from the two different dogs. These two dogs are not the same strength, and they're not producing the waves in similar strength. That means the waves coming from the different dogs, they're not in same phase and same monochromatic phase. When they're matching each other in the middle, they're making a destructive type of wave patterns, and because of that we can see less number of ripples in the middle. And this is a very beautiful picture to just to correlate in the in our lecture today whatever we have discussed. And the second example I can say, many times we have seen many laser show. Okay, and the laser show in many markets or some functions, and in laser show we can create many patterns of any pictures or any flowers or any kind of sort of things we can create. So that is happening because of the monochromatic and single phase nature of this light associated with laser. This is not possible to create from the normal lights, because the normal lights, all the waves, they're neither monochromatic, neither in single phases. Okay, and you can more knowledge you can gather what is monochromatic. What is monochromatic means there is single frequency. Okay, all the waves have single frequency, and phases means all their harms and the downs, they're matching exactly, where we can say they are in single phases. Anyway, so how the X-ray is produced, you can explore how the X-ray is produced. X-ray is produced just by using a cathode-like setups. Okay, and taking as a source, and when you use a cathode with high voltages, making one source as a positive and one source negative, the high speed electrons actually they comes from cathode and hits to the source, and by hitting the source you can create a lot of X-ray. Okay, this is very simple. But during this, whatever source you are using, based on that you can create soft X-ray or very hard X-ray. That means very powerful X-ray and very soft X-ray also you can use. And you can also interact. When X-ray interacts, let's say you have successfully produced the X-ray, and how you are interacting with the X-ray with metals. If you see, because X-ray you can just treat as a light, but also each light has some particle character based on the physics, but we are not going to the particle character of the X-ray. Just here we are treating the X-ray as only lights. Okay, if you treat as a particles, then again some lot of science will come into picture, but we are not going to that. But X-ray as a light, if you interact with matter, there are two different type of phenomena actually occurs. Either it will transmit in the entire matters, or it will scatter. Okay, and the scattering is called sometimes coherent scattering. Okay, we call it coherent scattering. And the correlation you can make that why we get our bones photograph using X-ray. Okay, muscles, lots, but only we get the structure of bones, not the other part of this body when we take the X-ray. So you can ask yourself, and you can find some answer. Maybe in the end of my lecture, I have given some clue for this. Why do we get photos of our bones only? Okay. And if I say what is the coherent electric scattering, let's say I will show some animation actually. Let's say X-ray comes and hits to the any atomic systems. Okay, when the X-ray hits to the atomic systems, what happens? The X-ray actually, the energy actually completely transferred to the atomic systems, and the atoms start vibrating in a more way as compared to the normal way the electrons are vibrating. Okay, and when the atoms they start vibrating, they create an unstable state in this matter. Okay, or any atoms or system they are vibrating, and they don't any system they don't want to stay in the any unstable state. Okay, so because of that they will emit some of the energy, and they again go back to their original state, and their emission, during that emission actually the X-ray has produced. Okay, and here that means X-ray came X-ray hit this system, and they create vibration in these atoms, and again the atom actually created X-ray and releasing that energy in form of X-ray. That means X-ray came and vibration, and then X-ray came. So this is called the electric scattering. That means here there is no loss of energy here. Okay, energy came and energy hit and created a disturbance or vibration within the atoms, and again the X-ray come into as emission. So that is called X-ray scattering. And in this case, this animation, I think it will give you a brief idea how the X-ray scattering occurs. Okay, so there is no loss of, and because of which X-ray method is a destructive method of analysis. Here, no harm is occurred to that particular system when you are bombarding with X-ray. Okay, but if you hit the any powerful X-ray, that may occur, but we are not going to that part of things. So now question comes that why the people thought of to get the atomic structure by X-ray. We have a huge range of electromagnetic radiation. We have microwave, we have radio waves, we have UV, but why the X-ray? Okay, the first initial the credit goes to those beautiful scientists. Actually, those they thought of about this, and this idea, the original idea actually came into picture. If you see, the wavelength of X-ray is around close to 1 angstrom. Okay, or maybe it will vary, but it will close to 1 angstrom. Okay, and most of the atomic distances, okay, the atomic distances, the spacing or interplanar distance that is d, that is also closely matches to the wavelength of X-ray. Okay, so these two correlation actually in the initial thought as came into mind of many scientists, that using X-ray we can get the information of atomic arrangement or the atomic structure. So because the wavelength of X-ray and the d-spacing of atom, they are exactly closely matching. Okay, so that initially a thought actually came into a breakthrough result in later stages. Okay, and here one correlation or one question I can put forward: do different elements matters? The answer is here, yes. The reason is that we have a lot of elements in the periodic table. Okay, and from this previous slide and this slide, you can came to know that when X-ray hits, the X-ray actually interacts with the electrons of the atom, not the core of the atom, because the X-ray cannot reach to the core of the system very easily. It interacts with the electrons. Okay, so if it interacts with the electrons, and we know all the elements, they don't have the similar number of electrons in their valency cell. They have different electron, have different number of electrons. So that interaction of X-ray with the different elements may vary. Okay, and if the interaction will vary, the scattering ray also will vary. So if the scattering ray will vary, we may get different information from different elements. Okay, so that is simply correlation that different element matters. Okay, and later stages I'll join these dots. Why I have emphasized this point here. Okay, and I assume all the students, they have some of the basic knowledge about the crystal and symmetry. Again, this is a huge topic I cannot cover in one lectures, but I can say maybe if anybody has some less knowledge, they can explore what is crystal, what is lattice, what is unit cell, asymmetric units, and we have 7 actually crystal systems, that is cubic, tetragonal, orthorhombic, hexagonal, monoclinic, and triclinic. And we have 14 Brevis lattice, what is point group, what is space group, all sort of things. But again, to that lecture, then they are not going to, even anybody don't know about much about these things, but again still you'll get a lot of information from today's lecture. And again, based on the atomic arrangements in each of these systems, that can be primitive or body centered or face centered and side centers. I think this information might have many people know what is primitive or simple cubic, we sometimes call, and body center, where we have every corner of atoms and one atom in the center of systems, and the phase center where we have the atoms in every corner as well as every center of phases. Okay, so that is called phase center. Okay, we simply sometimes call FCC, BCC, and these are sometimes the symbol also got used. And this is we can get the possible atomic arrangement of whether P or I or F type for different crystal systems I have shown here. So this is a basic idea of the crystalline symmetry. But again, this will help us in maybe later stages in my second lectures. I will discuss some of the things about more about these things. Okay. And if you see the single crystals, okay, many times we see in our kitchen, let's say if you find, we can find sometimes sugar, sometimes salt, and many times in our day-to-day life we come across with crystals. Okay, so what is crystals actually? The crystals actually it is a long range order, and basic difference between crystal amorphous you can very easily distinguish where there is a long range order of arrangement. If any systems we call them as crystals, or repeated or long range order we call them, and if there is no long range order then we can call them amorphous. Okay, and if you see any crystal, let's say some 1 millimeter, 2 millimeter crystals, how many atoms you can expect in such small crystals? Okay, 1 millimeter is around we know it is around 10 to the 7 angstroms. Okay, and assuming the atomic distance is 1 angstrom, that means almost we can have in 1 millimeter crystals we can have 10 lakhs of atoms. Just imagine. Okay, small crystals we can have in any one direction, you can have 10 lakhs of atoms. They have arranged not 1 or 2, 10 lakhs of atoms. Okay, so that is the idea of a crystal, just to give a brief idea how originally we feel and how actually they have. And in 10 lakhs of atoms, if in just 1 millimeter of distance area, these atoms are arranged. And we believe that all the atoms, we can create a lot of imaginary planes in any sort of atomic arrangements. And these planes can be drawn, assuming, but actually there is no planes. Okay, remember there is no planes, but we assume that all the atoms, they are arranged in a crystal planes, and because they help us to understand this crystallography more easily. Okay, but remember there is no actually there is no existence of such planes. This is just a numerical way of explaining. Okay, anyway, and what is Miller indices? The Miller indices actually, this is a notation. Okay, this is a 3-number notation. Okay, this is a 3-number notation which gives some information about some crystal planes. Okay, and as well as their directions. Okay, so remember Miller indices, it is just 3-letter numbers. It can be 100 or 110 or 11, or their family of also we can sometimes write. And these Miller indices, they gave the idea of about the plane, which plane and its direction. Both things we can came to know. Okay, at a time. And these some of the crystal planes are have drawn here. You can easily correlate in different, whether it is primitive or cubic or phasic. And while writing, you should be very careful. Okay, while writing any Miller indices, you should be very careful that whether you are going to give a normal bracket or a square bracket or this less than or greater than symbol, in this form you have to write. So the answer, based on my questions, I can answer that each notation have different meaning. Okay, you should not confuse, and also you should not use wherever. I'm just giving as a homework to all the students to identify, to explore what is the different meaning of this square bracket or the normal bracket and all sort of things. But remember, they gave different information about this plane. Okay, they, sometimes, especially in the below part, okay, they will give some direction about this plane. Okay, and sometimes the upper part they just about the plane, but the direction you can get from the below part. Okay, but these are some hints, but more you should explore what is the meaning of these notations. Okay. Anyway, so so far I think I have convinced you so far, to all of you, that when X-ray interacts with any type of matters, actually the X-ray interacts with the atoms, and the atoms, inside the atom, the X-ray interacts with the electrons, and we assume that all the atoms, they have arranged in a planes, okay, different planes, and that means when the X-ray will hit to the atoms, the X-ray will diffract from the planes. Okay, so this is the so far the conclusion, the progressive conclusion so far we have done so far. And you'll see all these, and one more thing also I want to highlight here, all the planes, they are presented in the systems, and you can combine them. That means all the planes can be also situated in the each crystal systems. Okay, that means 100 also will be there, 110 will be there, 11 will also there in the single system will be there. That means in each crystals or in each cubic systems or any unit cell, okay, the all sort of planes will be existed. And one important thing you have to remember here, the direction of this each plane, they are not same. Okay, the direction of planes is not same, and we have different planes. Okay, so that two conclusion we should take from this slide to the next slide. Okay, we have many planes, and each of those family of planes, the family of planes, they have similar direction. Remember, the family of planes, they have similar direction, they are parallel to each other. But if they are not family of planes, they are different family of planes, they have different directions. Remember, so that is the conclusion you have to take from this slide to next slide. And remember, when we have different set of planes, okay, let's say we have 200 plane, or we have 202 plane, or 132 plane. So all these different planes, when the X-ray will hit, they will diffract, because each of those, we assume that each of these planes, they have all the atoms are arranged in a plane. Okay, or wherever you will find the atoms, wherever plane will be there, the atoms will be there, because wherever atoms will be there, the electrons will be there, the X-ray will interact with the electrons. Okay, and in this slide you can see by comparing the three comparison, 200, 202 and 132, two things you can observe. The first thing, the direction of diffraction is not same. Okay, all the three planes, the direction of diffraction is not same. Some point is going left, some point is going right, and some point is above. And second point also, you can see the intensity of the diffracted spot also is not same. Sometimes it's very small, sometimes it's very large. Okay, so where it is coming, that point also already I explained. Because in all those planes, first of all these planes are not in similar direction. So as they are not similar direction, the diffraction also will not be similar direction. There will be different direction for all the planes. That is clear. Second, why the intensity of these spots, they are not same. Okay, sometimes the intensity is very small, sometimes the intensity is very high, because all these planes, they don't have the similar number of atoms. Okay, some plane may have more number of atoms. More number of atoms means more number of electrons, so diffraction may be higher there. Okay, so there you will get a brighter spot. But where in any plane where we have the less number of atoms, there you can expect a very weaker spot. So that actually, because of which we get different weaker spots. So now let us combine all these concepts. Okay, let us assume that a crystal have many different family of planes, and we assume that all the family of planes we combine, because they all exist in the same crystals. And when X-ray hits, X-ray can distinguish which plane it is interacting, we get a lot of diffraction spots. When the X-ray hits, yeah, there is some disturbances. Yeah, when the X-ray actually hits to the crystal, we got many spots at a time. Okay, but remember, all these spots are related to some different type of family of planes, and the spot intensity, they are different. They are related to, because each plane have different number of atoms, because each number of atoms, they don't have similar electrons, electronic arrangement. They have different arrangement, different number of atoms. Because of that, all sort of these beautiful patterns or the different type of spots we created. So that's why here the two important message we are going to take from this slide, that the position of the diffraction spot and intensity of the diffractive spot, they may vary because the planes are not similar direction and they don't have similar number of atoms. Okay, so that is the conclusion so far. Okay, so assuming that in this slide, maybe in this slide I will explain that why different plane have different intensity of spots. Okay, just to give some idea that in the left side and the below part, I have shown two structure, one FCC structure, the two side FCC, and one BCC structure I have shown. Okay, so assuming the planes are drawn here, and you can see in the FCC plane, in this upper plane you have 5 atoms, but in the BCC you have 4 atoms. So if you compare a BCC with FCC diffraction pattern, X-ray go the right side of this right side, the X-ray comes and this goes, you'll not have the similar type of number of atoms in this plane and in the BCC and the FCC, and because of which the diffracted ray, and here the diffracted ray I have shown here 1, 2, 3, and here you can see the 1, 2, they may have similar pattern, but the 3 which is coming from the center of the BCC, that diffracted ray is similar property, because that don't have any atoms, very few number of atoms are there. So the diffracted may or may not be same with the others. So that's actually varies your ultimately your spot as well as the direction of your when they to the decay plate. And also you can correlate that within the crystals there are many planes exist, and the all the planes or the family of planes, you can say, they don't have the similar direction. They have different directions, and when the X-ray will hit to each of these family to diffract the ray in a similar or send the diffract ray in a diffraction in a single position, but rather in a scattered manner to here and there. Okay, so this is all about the how the X-ray scatters inside the atomic planes or inside the atoms. So that's why the next we are going to discuss what is the Bragg's law or the Bragg's diffraction. So as I told, the X-ray was discovered in 1901. Okay, because Röntgen got the Nobel Prize in 1901, but Bragg got the Nobel Prize in 1915, I think. Yes, he got the Nobel Prize in 1915. That means after discovery of X-ray, it took almost 15 years. Okay, to make some full information using the X-ray. Okay, so that's why the history part I discussed. You can correlate how or how many years actually they took. And whenever we discuss about Bragg's diffraction, the equation actually comes into picture, that is 2d sin theta is equal to n lambda, or n lambda is equal to 2d sin theta. What is the significance of the symbols? The 2 is a constant, and d is the interplanar distance. It is shown assuming all the atoms they are in a similar planes. One is below, another is top, and the distance between the two planes is equal to d. Okay, what is theta? Theta is the angle of incident where it is hitting to the crystals. The X-ray is hitting to the crystal with the angle of theta. And what is lambda? Lambda is the wavelength of the X-ray which is coming. And remember, the X-ray of wavelength can vary. Okay, even the X-ray also, there are a lot of X-ray, soft X-ray, hard X-ray, and based on that the wavelength also can vary. Okay, but again it is very close to that 1 angstrom, maybe 0.75, 8, or sometimes 1, like that. What is the n? N is the order of diffraction. What is the order of diffraction we'll discuss maybe after a few maybe next slide or this slide. I will explain what is N. Okay, so let us try to understand very simplest manner what is the Bragg's did actually. Bragg, they did the experiment already. I told the father and son they are doing the experiment, but later conclusion came to picture. Bragg thought of that all these crystal planes, okay, these blue dots, okay, these are the atomic positions, and the line, straight line along these atoms, then this is the plane. Okay, let's say the monochromatic X-ray X-rays are coming and they are hitting some of these planes. Okay, the first plane also hitting, and some of the X-ray is also hitting to the second planes. Okay, so what happens? The X-ray hits and they diffracted. Already how the X-ray scatters. Already I told this is electric scattering. There is no loss of energy, but the only direction of the X-ray has changed because of this interaction with the atoms. Okay, and the second wave also hits to the second layer of this plane, and again it is diffracted in a similar fashion. Picture. Let's say the AC has drawn AC a perpendicular has drawn here, and similarly AD perpendicular drawn to this the second wave, diffracted wave. Why have done this perpendicular? Assume that all the institute all exactly in the similar phases. Okay, a diffracted ray from A point to onwards and to D point onwards, they are exactly in the similar phases. Okay, the similar phases, the horns are matching, the down portions are matching. Okay, we call it thrust and crest. So they are exactly matching, and they are in similar phases. And we know when the similar phases, that is a constructive wave creates, and we will got a very bigger spot. Okay, so that is idea actually. Okay. What happens to the middle part, that is up to C to D? We don't know. Okay, what is the C to D occurs? Why it is happening? We don't know. Okay, so that is about the Bragg's law. So what happens? So the next and this C to D, this is the extra length actually covered by this second wave. Okay, not the first X-ray, but rather the second X-ray is covering the extra length because it is hitting to the second plane of this atom. Okay, the first ray is not going that extra distance, but the second X-ray is covering some extra distances. Okay, so without going any mathematical point, just I want to highlight, if the extra length, let's say C and D, okay, this will be exactly multiple of either one wavelength or two wavelength or three wavelength, then only we can get from A and D point the waves will be in similar phases. Okay, or they will create a constructive wave. Okay, there will be only constructive wave. The initial wave up to C up to A, they are constructive, they are same phases. A onwards and from D onwards are similar phases, but we don't know to C to D. And the Bragg's law says that this only if from C to D, okay, from C to D, that length is exactly matching with either wavelength or two wavelength or three wavelength or any multiple of wavelength, then only we can contribute. That is the Bragg. Okay, now to understand this, okay, the to D we call as path difference. We call as path difference. The path difference can be from C to B. It can be either a half wavelength. If it is half wavelength, the next also will be half wavelength. That means total path difference will be one wavelength. And if C to B it is a complete wave, then the B to D also will have one complete wave. Then the total path difference will be two wavelength. Okay. So that is all about the Bragg's diffraction. Okay. So now you can make another correlation. If I will make another third line here, okay, and you can make a third line here, you can assume that the third line again have to cover a longer distance as compared to the first and second, because you can expect that the angle of incident will be slightly will change for these, and the third wavelength again is going to be a longer distance it has to cover. Okay, and the derivation of and here I think I always encourage to the students, you always should correlate yourself to nature. Okay, sometimes nature, whether it's Bragg's law or any kind of studies, I feel myself, and I always try to correlate many things. And very small incident I am saying, in my childhood days, I belongs to Orissa. Okay, and in my state there is a lot of production of paddy. Okay, and this paddy actually in a very economical way, people what they do, they put this paddy here to harvest, and whatever the bullocks they have, they combine all the bullocks and they keep on rounding in around one middle point, and as soon as the bullocks they keep on rounding, they because of their weight, the paddy actually discharges from the straw, and you can easily harvest. And from this picture, why I am showing this picture, and this picture has a correlation to this Bragg's law. Okay, I'm giving some clue. You try to find out what is the to this Bragg's law. Okay, there is no direct correlation, but there has some correlation to this Bragg's law. Okay. And here in this slide, I am showing how we can derive this Bragg's equation, that is 2d sine theta is equal to n lambda. Okay, and here as you can see, this theta is defined here, and based on these perpendicular triangles. Okay, and you can create the what is CB, what is the CB value will be d sine theta, and the ADB, either ADB or ACB. Okay, the idea is that you can create the value of dB in terms of d, because d already defined, okay, which is AB. Okay, and the dB value will be d sine theta, and if you put all these CB and dB, because CB and dB or the total CD is the path difference. Okay, so these two path difference actually are finding, and each dB or CB, this value will be d sine theta, and if you add them, there will be 2 d sine theta. Okay, d sine theta is equal to 2 d sine theta is equal to n lambda. Okay, so that is all about your Bragg's diffraction. So Bragg diffraction, and here the n is defined here. Okay, n is here for the first layer of atoms. Okay, the first plane of atoms, your n value will be 0. Okay, and or 0. Like that, you can have n value of 0, either 1 or 2 or 3, but it will not be in fraction way. If it got fraction, then your constructive wave is not going to form, and rather than it will going to be a destructive wave. Okay, and destructive wave, you know, the destructive wave always cannot reach to the target. Okay, so that is all about your Bragg's diffraction. This is a very simplest way I try to explain, because there are many biological students or medical students, they may not go to the details, but again, for both the students, I have the entire things I have written, and they can go through this. So let us, so far, what do you conclude on the Bragg's equation? It gives how the path difference, it should be multiple of X-ray, so that we can have the constructive wave after each diffraction. And constructive waves, they can reach to the target very easily, or we can in other words, we can easily identify them. Okay, the second person actually before Bragg's, because he got the Nobel Prize in 1914, and Bragg's got the Nobel Prize in 1915. That means Lau, Bragg's, and they are working same time, you can say, after the discovery of X-ray. And Lau method and Lau's method and the Bragg's method, they are almost similar. Okay, but their assumption was different. The only assumption is that the Lau, he was considering the atoms as diffraction from individual atoms, and Bragg was considering the entire atoms as a plane or the atomic arrangement as a plane. That means diffraction occurring from planes, and now they are considering the diffraction occurring from individual atoms, but in three-dimensional way. Okay, the Lau method and Bragg's method, they're not much different, but they're almost similar, you can say. And here I have shown a principle of Lau methods. Again, there are a lot of mathematical part in the left hand side, but again I am not going don't see that part because you'll make a lot of confusion here. But again here also you can see sorry, there is some mistake here. Okay, so here what I am to show here, you can see Lau only difference is that they consider that only the atoms as a your center of diffraction of X-ray. That means when X-ray hits to the atoms, okay, here also the same way you can consider the X-ray came into here and hit this atom, center of the atoms, and after that the X-ray diffracted, which is shown as a orange arrow. Okay, the blue arrow as incident X-ray and the orange arrow as the your scattered X-ray. Okay, and here, and we assume that the waves which are coming to before hit the atoms, and we assume that the atoms are up to m for the second wave, and for the first wave that is already reaching to the atom A, and the waves are in similar phases. Okay, similarly the diffracted ray from B and from N, okay, they are in similar phases. But what happening to A to N and what happening to B to M? Okay, so that total difference if you see, okay, so that difference is the path difference here. Okay, that difference is the path difference, that is AN minus BM, it will be your path difference. Okay, the exactly way the Bragg did, here also they use the mathematical equations and they find the last equation for each of these, and remember this Lau method, they consider the atomic arrangement, this is one direction only. Okay, and if for this one direction they got a equation, final equation, as you can see, the entire mathematical derivation you can go one by one because we don't have much time here, but it is very simple, you can say one by step. This is just the right angle equation they have used. Okay, and they have got the equation where for any one directions, okay, you can get A alpha minus alpha 0 is equal to n lambda. Okay, and alpha 0, these are the your the value of cos theta 0, they have taken a value of alpha 0, and the cos theta they have taken as alpha. And what is theta 0, alpha 0? They are the incident ray angle and the diffracted angles. Okay, for different rays they have taken. Okay, so based on this you can get this equation. So what is your in this equation, what are known, what are unknown? Okay, for any crystal systems, the A is constant, that is the unit cell. Okay, unit cell length, that is constant. Your lambda value also constant because you are sending each time a monochromatic X-ray whose wavelength must be fixed. Okay, and your only variation is theta. Okay, theta variations, and theta varies, and then they have a good correlation here. So this is again the last method, but the I don't think any difference between Lau and the Bragg. They assume the system as a into different way. That's all the but the all the principle they have the similar consequences or the answers. Okay, and we'll move to this powder diffraction. Okay, and the powder diffraction, the principle of X-ray diffraction was developed very nicely. But now the next question comes into picture: how to useful, how to get this entire experiment or the method to get some useful information about the or the application part of this X-ray diffraction. Okay, and for that we need to develop a instrumental setup. Okay, and the first credit goes to this Debye and Sitcher experiment. Okay, they actually created a instrument setup. Okay, to create these diffraction patterns, because theory part is okay. Okay, but when you come to this practical part, you have to be instrument setup where you can get the results very quickly and you can analyze them. So that credit actually goes to this device experiment where they have created a basic setup for the powder diffraction setup. Okay, and latter stages actually the single crystal developed, but powder was developed very early. And as you can see, they have a lot of crystals they have taken. There's not a single crystals, and each of the crystals you can see these some planes I have shown here. Maybe these are family of planes, but due to arrangement of the crystal, they have, all the crystals they are not arranged in a similar fashion. They have different orientations, and due to different orientation, you can see this. Even if family of planes, they are not now in the similar direction. So now you can assume, even though these family of planes, they will they're supposed to create a similar type of X-ray patterns, but now they are not. They will not show the similar patterns because their orientation is not same. Okay, so they will be scattered the wave in a very unusual manner in all sort of 360 degree they will diffract. Okay, but again, is it possible to capture all the diffraction? Again, it is very difficult. Okay, now a circular photographic film as crystal, and I think they assume that from this film whatever information we will get, that will be enough to create the informations, or you can get the maximum diffractions from this photographic plate, because we assume that all the diffraction which are hitting to the photographic plates, they are based on the Bragg's diffraction and coherent scattering, or the or you can say they are constructive waves in form of constructive waves they are hitting, and you'll get some information. So this is basic setup they did. And after the experiment, actually, what happened? You see, the result they got like this. Okay, this blue, the blue color setup. You can see the photographic plates, and where you can see there is some curvature, like some diffracted spot actually created. How this created actually? You can imagine this photographic plate which is shown in a black ribbon-like color. Okay, a ribbon-like structure. This after the diffraction, if you expand this the ribbon, then it will look like this. Okay, and where you will have two dark spots, and these spots are where the X-ray is entering, and the other one is X-ray is existing. Is exit X-ray. That means X-ray is hitting or going out of this film to the other side. But as I told, when the crystals are in the middle and they don't have the similar orientation for all the crystals, so they are going to make several such type of cones, okay, in various directions. And now the question comes, why the different type of cones? Okay, the different type of cones, because we have different type of planes. Okay, and different type of planes, they don't have the similar arrangement within the crystals. Already we have discussed. So because of that, the diffraction angle is going to be changed. Okay, their diffraction angle is going to be changed for different planes. Okay, but the similar planes, maybe the cone size will be same, but again they are not be in the similar direction, because all the crystals, they don't have in a similar arrangement, or the lying in this powder crystals. So that's why there is all possible number of cones they are going to form. But again, the result will be this much. Okay, as I have shown in this in the blue strip in the below part, this is your result. Now question comes, how we are going to analyze this powder pattern, and how to get the structure of this molecule from this pattern. There is no information here. But the answer is, there is a lot of information is there. Okay, if you can correlate, we can get many information from this. And now slowly we'll go, and I'll give you some hints how we can get the information. First of all, the different cones, they are forming because of different crystal planes, that you should clear. Okay, because the crystal planes, they have different arrangement within the crystals, and they will diffract the X-ray in a different angle, because the crystal planes, they don't have the similar arrangement within the crystal lattice. Okay, that's why the angle will vary. Maybe for this blue angle, as I have shown here, maybe for theta, and for this red cone, you have the angle of theta 2. Okay, so like that, we have different theta for different cones. Okay, so this is your the first conclusion so far from this slide. Okay, so now we'll try to analyze this powder data. It is very simple. Okay, so now let us see. We'll take one set of this blue strips photographic sheet I have shown here, and you can see all these the curves. Okay, the similar type of curves around these central points, they have they have derived from this a single cone. Okay, the single cone means the single cone is again relevant to a similar set of family of planes. Okay, and the similar family of planes, they have similar arrangement or the angles, so that's why let's say it is theta 1 theta 1. For the next family of planes, let's say theta 2, and the next family of planes, let's say theta 3. So like this, these cones, they are nothing but they represent the family of planes arranged within the atoms. Okay, then now the next question comes, how this is again useful. Yes, what I did, I just take only one cone, let's say. Okay, I'm here, I have created one crystal here, and I assume that the X-ray is coming and hitting to this the crystal, and the diffracted rays are going in different directions, and they're forming cones. And if you see, very interesting things here, when the X-ray is coming and hitting, okay, diffracted rays are going, but the X-ray is hitting to the crystal in form of theta. The diffracted ray also, it is theta. But if you see the whole cone, okay, the whole cone, okay, the gap is 4 theta, because the X-ray is coming and entering, going to the other side. This is already 180, so the 180, another 180 below. Okay, so or you can correlate in form of theta. Okay, this is theta, and the another 2 theta also will be there. So that's why the entire if I consider as a arc here, where the r is the distance from the central part of the crystal to the radius of this cone, okay, or the curvature part, that is r, and the entire angle will be 4 theta, and your the arc part, which is the length of this arc, let's say, is equal to s. Okay, and there is a very good relations between this any arc having a radius r, and your angle of this radius is 4 theta, and its arc length is s. So the 4 theta is equal to s by r. Okay, and the theta will be s by 4r, which is represented as radian, but again you can convert to this theta value in form of degree by multiplying 180 by pi. Okay, so that means the theta value we can get. So what conclusion so far we got? That means from these diffraction patterns, we can get the value of theta. Okay, by simply measuring scale. You can measure it by using scale. You can measure, okay, the arc size, and the radius also you can measure, and by which because the radius you can measure how, because this distance of crystals to the your photographic plate where it is hitting. Okay, that is r. Okay, so by measuring r and s, okay, you can get the value of theta. Okay, simple equations. Okay, so now question comes, let's say we got the value of theta from this diffraction pattern. Okay, so now what is next? Okay, the next we'll use the Bragg's law. Okay, the Bragg's law, we know the n lambda is equal to 2d sine theta. Okay, and each of these the d also can be defined as 2 sine theta by n lambda. Okay, and from these also we have a correlation that each of the unit cell, whether it is the 7 crystal systems, whether it is triclinic, monoclinic, cubic, all the systems, they have a direct correlation of their D spacing, that is interplanar distance of their D and with respect to A and the HKL. Okay, this is already known. Again, this is another lecture maybe need I to basics to about the symmetry, but again I am not going to discuss here. But I will give you details about this the entire all relations here in the slide, and you can go back and you can correlate how these each systems, whether it's cubic, tetragonal, orthorhombic, they're very straightforward. And here it shows the relation between these your ABC. ABC means your unit cell length. Okay, that is ABC, and D is the interplanar distance, and the Miller indices are HKL. Okay, this is all about this plane and the unit cell, and they are very correlation for each of the system. This is already standardized. Okay, no need to worry about this. But how they have derived, you can go back to any basic crystallography systems or any solid state books. You can find this correlation how they have derived. Okay, so I'm not going to that all details, but you will see the cubic, tetragonal, or orthorhombic system. They are very straightforward. But for monoclinic, hexagonal, triclinic, and trigonal, they are a little bit complicated, but they are not. They have a standardized process. So what we are going to do from this powder diffraction, what we got so far, we got only value of theta. That's all, nothing. We got only theta by measuring the arc size and this radius. We got the value of theta. That's all. We don't have any other information. But again, how we'll get it? But complete picture of that crystal, how we'll get it? So let's say we'll expand the Bragg's law a little bit further. Okay, the Bragg's law what shows the n lambda is equal to 2d sine theta. Okay, and remember the 2d sine theta, that means it is the theta related to individual h scale. That means individual planes. Different plane may have different theta. That's all. Okay, so here the h scale I have written because each theta is coming from each plane. Okay, so whenever you define different planes, the theta value may change. Okay, that's why I have defined here h scale. So n lambda is equal to 2d sine theta. So both sides I have just put the squares. Okay, and from this value or this from this cubic relations of D and h scale and A, this value I put here. This D value actually I have derived from this cubic side, from this left side, and this D value I put here, and again I square. Okay, and this the value is going to be 4a square sine square theta by h square k square l square. This is very simple. You can do it slowly. And then again I simplify what is sine square theta. What is sine square theta is equal to lambda square by 4a square is into l square h square k square l square. Okay, so and you assume that and you already fixed that lambda for any diffraction it is fixed because the wavelength of X-ray we fixed, we keep as a monochromatic X-ray. The lambda value never changes. And A for any crystal system, the A must be fixed. For any cubic system, the A must be fixed. It may vary from crystal to crystal, from different compounds, but any cubic system, the A will be same for all. Okay, that means lambda is fixed, 4 is constant, A is constant. That means the entire parameter will be constant. So let's say the parameter I am writing as a K. Okay, into multiply by h square k square l square, because this may vary because for different planes within the crystals. So this is the simplest form I derived from the Bragg's law based on this value putting from this cubic system. So now what I did, I am just taking the possible h scale value. Let's say I am taking the possible h scale value as 100, and I'll get the value of h square k square as 1k, 2k, 3k, 4k, 5k. But you will be surprising, you will see for 7k there will be no possible values. Okay, try to find out why there is no possible value for 7k. Okay, it is missing because there is no other possibility to create the value, because it will go again fraction type something. Okay, because in and the missing part will be 7k. But again you will continue for 200. Again you can go for 3000, 310, 320, like that. You keep on going. Okay, and these values, this k value don't have any significance here, but it will help us to analyze some of the powder diffraction patterns. Maybe in the next slides I will explain. So far I can explain here that what is powder diffraction and how the powder diffraction pattern actually comes in, looks like, and from this powder diffraction what we got the information, the only information of theta. Okay, and from theta again we from Bragg's equation we have modified the equation in form of sine square theta, and sine square theta we got in form of k. Okay, and now from the all possible of scale we got this value of k. So now what is next? The next you see this is the powder diffraction pattern for a simple cubic or BCC or FCC. Okay, so what is this? And now you'll not ask me what is 1K, 2K, 3K, because the previous slide I have already explained, and they are directly related to this sine square theta. Okay, the 1K, 2K, 3K, 4K, or they'll keep on going from 9K. After that also you can have possible values. And each of these 1K, they are associated with some planes. The 100 plane, 110 plane, 11 plane, 200 plane, and this like this. Okay, so now this is your fingerprint, you can say. Okay, by comparing this you can analyze any powder pattern, and you can easily say whether it is going to be a simple cubic or BCC or FCC. Okay, so now let us see one very closely. We'll see, and you'll see for single cubic you can see there is every for 1K you will have one peak, for 2K you will have one peak, 3K, 4K, 7. That means every K, but 7K already I told this is by default it is missing for all. Okay, so 7K you don't worry for 7K, but except 7K you'll have for all K's values. That means the all K values means they're corresponding to some theta. Okay, remember. Okay, this K just for notation, for helping to understand this, I have just noted the K, but this K here have no values. They're directly related to some theta. But here you can see this K value for 1K, 2K, 3K, every K we have some signature here. So that is a simple cubic. What about BCC? Okay, BCC we got only for 2K. We will got next the key peak for 4K, and next for 6K, and next for 8K. Okay, like this you will get from BCC. And for FCC what you will get? You will get for 3K, one you will get from 4K, and in between there is no, and again you will get for 8K. Okay, so what is the significance of this? Okay, how will this pattern or this fingerprint will help me to identify? The answer is very clear. If you see in a single cubic, wherever the peaks are arising here, okay, they have a constant differences. Okay, the constant difference is nothing but K. Okay, so if you get any patterns where the peak difference, okay, that the theta from next theta to next peak, okay, you'll get the value of K. So you can easily identify this peak is coming from simple cubic. What about BCC? BCC also we have similar correlation, that in BCC wherever you get the peaks, you'll have the peak of 2K difference. Okay, if you got the difference of 2K, then you can correlate that the peaks are coming from BCC. Okay, so like this you have some of the possibility, and for interestingly for 9K you have two possibility, whether it is from 300 or 221. Again you can correlate from theta, we can easily identify. So this is some basic way of analyzing the powder diffraction, but there are multiple way, very hard methods to distinguish the complicated powder patterns also. But today hello madam,
Yes, sir. Yes, sir.
break or we'll continue? How the students are?
Sir, you may continue.
Okay, yeah, maybe we'll few slides we'll
Okay, sir, no problem.
yeah, sure. Okay, so now this basic pattern, and now we'll my next few slides we will try to understand some of the original structure of NaCl, and as per the your course has designed or they have requested, madam has requested, we'll see. So here I have shown the original powder pattern of a NaCl. Okay, sodium chloride. This is the original pattern of a NaCl. Okay, I have shown here. Let's say we don't know what is the structure of NaCl, but we did the experiment, we did the powder diffraction pattern, and we got this peak. Okay, and let's say how these peak positions are defined. This is 11020. They have some another discussion, but assume for the timing that these peak positions and here this is the typical pattern of any powder XID experiment you do. This they should look like, and here are two parameters. The one parameter, the x-axis is 2 theta, and your the y-axis has the intensity. Okay, intensity here we don't worry for the intensity. And now already I told why the intensity varies, because in each of these planes we don't have the similar number of atoms. Okay, where more number of atoms, you will expect the diffraction pattern will be strength or stronger, and you will get the more intensity peak there. Okay, so that is all about here. So here you can see that this is the powder pattern of a typical sodium chloride, but we don't know what is the structure of sodium chloride. Okay, whether it is FCC or BCC, but or simple cubic, we don't know. Okay, so now let us bring our the fingerprint pattern we have developed just before this, or the correlation patterns. So now you start correlating here. Okay, from this original PXID pattern to this. Okay, so now you can see the planes are already defined in the sodium chloride. Okay, this is first the peak is coming from 111. So A11 is coming from 3K. Okay, and the second one is coming 200. Okay, and the second one here, the FCC plane, it is exactly coming from 4K, that is 200. The next plane, there is no point or no peak, and the second peak is coming from your 220. Okay, and it is already defined here. Okay, so now you'll exactly match to this point here. Okay, and also you can check the gap also. Okay, now you see from your 3K to your 4K, the 3K to 4K, your gap will be whatever gap, and from the 4K to 8K, the next peak is coming to 4K, that is 220. That gap you see, that gap itself, it will show whether it is FCC or BCC, or you can correlate whether it is 2K, 3K, 4K. Okay, and now you can you'll be agree with me that without comparing this the fingerprint pattern which you have developed based on this theory and the original NaCl pattern, we can say this is a FCC structure. Okay, this is a FCC crystal structure, but we have just defined only 9K, but this is not only 9K, you can go for further, because there is no limitation of the planes in the crystals, and you can go, let's say, the 511. That means 511 means 5 square plus 1 square plus 1 square. You can create so many the scale values. Okay, so like this. So you can easily, this is verification of NaCl powder pattern, that is FCC structure. And originally the sodium chloride is a FCC structure, as shown here, and that each alternate that is arrangement, that is, if you see only the sodium chloride, sodium, either to take the blue spots as sodium, or the chloride as a red, or vice versa, whatever you can say, they are uniform. Okay, so if you see all the sodium, they are in FCC, and all the chlorides also, if you see, they are also in FCC. Okay, both the chlorides and sodium wise, this they are in FCC. That's why the sodium chloride structure is a FCC structure. Let's say we'll go to the next structure. Okay, the next structure, the potassium chloride. Okay, potassium chloride also, you'll be surprised, this potassium chloride also, it is a FCC structure. Okay, it is a FCC structure. Okay, the Potassium chloride also is FC structure. I am not defining here which one potassium. Let's say you assume whatever potassium soda. It is also FC structure. But surprisingly, this potassium chloride will not exactly match to the sodium chloride structure or the PXID pattern. Okay. And if you see, here you see, for FCC, this 111, okay, the 11 plane supposed to come in FCC, but this 111 reflection, that is 3K reflection, is missing in potassium chloride. Surprisingly, is missing. But after that, the other values are there. Okay, the first it is there, 200 is there. Okay, 11 is missing, 3K is missing for potassium chloride, but rest of the peaks are there. That is 200 is there, that is 4K is there, next K, 8K is there, and the rest higher order planes also exist there, and you can expect where it is there. Now question comes, why this the 3K value is missing here? But FCC, as for the fingerprint, we should get one peak for 3K, that is 111. Now I'll leave this for students to try to correlate. Okay, what is happening? All the time, the theory is not the only explanation for this. There's some logic also, it is there, you should apply. And what is the logic here? The sodium chloride, if you compare the sodium chloride and potassium chloride, in the clue I have given here in the left side, if you see the potassium chloride, and in the potassium chloride, potassium stay as potassium plus and chlorine as minus, and both the potassium and chlorine, they have exactly 8 electron systems. Okay, and when the 8 electron systems are there, okay, and assume they are FCC, that they are actually FCC, but in the powder pattern, one of the peak is missing. Okay, so only you can correlate to the diffraction pattern. When the diffraction pattern originate, okay, you will get the answer. The answer is that in your due to exact similar number of electrons in potassium plus and chlorine minus, so when the X-ray hits, okay, so the wave pattern will be exactly similar, because X-ray is hitting to the equal number of isoelectronic systems. So in the isoelectronic systems, okay, when the diffracted ray will generate, okay, so those if they are not coming from the same planes, they may destructively interfere, and they destructively interfere, and they may in such a extent that they will dissolve completely, they will make zero. Okay, because one is coming from isoelectronic systems and they will cancel each other. Okay, so because of that cancellation, you are missing here this 110. But why not, if the same logic if we put here, why we are getting in the sodium chloride? Yes, you are getting sodium chloride because your sodium chloride systems, your sodium chloride is not a isoelectronic systems. Okay, sodium chloride is not a isoelectronic systems. Okay, let's say I'll write here, this is your sodium plus and chlorine minus. Sodium, it will be your, how much electron will be? I think it will be 10 electron. Okay, so here your sodium will be 10 electron and chlorine will be 18 electrons. That's why these diffraction, they are not isoelectronic systems. So the diffracted ray from different planes, from sodium planes and the chlorine planes, they are not going to be same, though they will cancel because they are the destructive wave, but they will not cancel each other exactly because they are not isolation systems. So that's why the peak is here. You can see the peak of 110, it is very small. That is, it is destructive wave. This peak is coming from a destructive wave pattern of diffraction, but it is not cancelling completely because you don't have a isoelectronic system here. But rather, in a potassium chloride cases, because of this in electronic systems, the diffracted ray coming from 110, they are cancelling each other, and it is completely missing for potassium chloride. Okay, now we'll correlate to the third structure, that is cesium chloride. And you can see the cesium chloride, this is original powder pattern of cesium chloride, and the planes are defined here 100, 110, and now you can correlate and you can say me that which one it is, and it is you'll see this cesium chloride you are getting a simple cubic systems, because you are getting for 100 plane, 110 plane, 111 plane, and 200 plane, and 210 and 211 like this you are getting. That means all peaks are coming for all k values, so that's why it is a simple cubic. But most of the students, they sometimes they assume that the cesium chloride is a BCC structure, but actually the cesium chloride is not a BCC structure. Okay, many of the even the students, or sometimes maybe wrong way of representatives we do, because by definition, if you see what is BCC, the central that central atom should be surrounding the atoms, the central atom and the surrounding atom. This must be same. Okay, if it is same, then only we can call this is a BCC. Okay, if there is no similar atoms, we cannot call as a BCC. Okay, so here in the cesium chloride structure, if you see, the cesium is inside the center of the cube, and in the each corner there are chlorides. That means the central part, the central atom, that is chloride, and surrounding atoms chlorine, they are not same. Okay, so now assume that this cesium is not. So now this the argument has cancelled now here, because they are not similar around the atoms, so that we cannot say this is a BCC. So if it is not BCC, what is that? Let's say assume there is no cesium here. So what is that? That is only chlorines. That is chlorine. They are packing only in the corner part of this. So that is the arrangement of simple cubic. So if you go to the only cesium also, you will get the same also, the same pattern. If you assume that there is no chlorine, only cesiums are there, by expanding this lattice, you'll get the, again, this is for simple cubic for cesium. So remember, cesium chloride, this is not a BCC structure, this is a simple cubic structure, because the PXRD pattern exactly matches to the your simple cubic form. Okay, so this is all about your verification of powder patterns. But as I told, this is a huge topic, and you need a lot of classes to identify them. And last, I think I'll stop here, my end of lecture here. But before that, I want to highlight here that we have a single crystal facility in our department, and I am the in charge of this single crystal facility. And I welcome all the students whoever participating here. I welcome to visit our to PU campus once, maybe one day or half day, if you are really interested to know all about the single crystal facility. And maybe I'll show how the diffraction occurs, how the instrument works, and if you can talk to your teachers, and anytime maybe some group of students also you can come, there is no issue. Those who are really interested to see how the machine works and the X-ray facility works, and I will take care all these to accommodate you for this learning process. So thank all for this, for giving me this wonderful time to interact with all of you. But I would love to be not the online version. Maybe sometimes I'll visit your college to give a direct interaction to all the students, because I'm missing this part to interact with the students from this online way. And I have given some lot of useful links. After this lecture, I'll share this slide to your mom and the principal mom, and he may share. And some of the very useful information I have shared regarding the instruments and a lot of the X-ray related things. You can go through it. And I'll stop here, and I welcome any answers or queries if you have. Thank you.
Thank you, sir, for your wonderful talk. Now I request participants to ask if you have any queries regarding this topic.
Yeah, you can ask any questions. It may be silly questions, but don't mind. You can ask. Then I'll feel good that you got something from my lecture. Any students? Yeah, actually, this facility we have created from DST. The students are joining through some class when there's some auditorium, or they are individually joining through their.
Sir, actually, students are joining through projector in seminar hall.
Acha, okay.
And participants from other colleges and institutes join through Google Meet.
Okay.
Dear participant, unmute yourself and you can ask any query regarding this topic. Or you can message in chat box.
Yeah. You can chat box also. Yeah, the PPT I will share after the lecture. I will share the entire PPT. There is no hidden things here for
Okay,
all your. Yes.
Okay, sir. Thank you, sir. Sir, I think there is no query. So let's move towards the end of session. Now I request Dr. Anita Rani, HOD, Department of Basic Sciences, to give vote of thanks to Dr. Subhash Chandra Sahu. Welcome, ma'am.
Thank you, Kirandish. Sir, actually, you had explained all the phenomena in detail, so that's why I think there is no query from the students. I am from the physics background, sir, and my area of research is also condensed matter physics, and this topic is also of my interest. So, I would like to.
Yes, ma'am. Actually, the thing is that you can go more detail also, but sometimes you have to skip to see who are the audience.
Yes, sir. Sir, actually, you had covered both the concept of physics and chemistry.
Yes, thank you.
So, I would like to express a warm and graceful morning to our most valued and honorable chief guest, Professor Subhash Sahu, Department of Chemistry, Punjab University, Chandigarh, and our worthy judges, my dear students, and all the participants present over here. I, on the behalf of Guru Nanak College, Shri Muktsar Sahib, Department of Basic Sciences, and all the entire fraternity of institution, first of all, I extend my sincere thanks to the Almighty God for making today's event a resounding success, and special thanks to our today's guest, Professor Sahu. Sir, you had explained all the phenomena related to diffraction, interaction of X-ray with matter, crystal structure in a very well-defined way. And it is also very interesting that you had correlate the phenomena with nature. And I hope all the students have enjoyed this session. And I congratulate to Madam Kirandish for organizing such an informative lecture, which will be helpful for all the BSc medical and non-medical students. I express my sincerest thanks to all the faculty members of the Department of Basic Sciences for their efforts for organizing and such a wonderful webinar. So thanks to all, and special thanks to sir for giving us such an information on these type of topics. And this is a very important topic of diffraction. And thank you, sir.
Okay, ma'am. So
thank you, ma'am. Thank you, ma'am. Thank you, sir, for this wonderful talk and to give us facility to visit your lab in Department of Chemistry, PU Chandigarh. Definitely, sir, we will arrange a visit of our students for their practical exposure.
Yes, ma'am. Yeah, because